Welcome to this first class for inequalities. So today we'll be talking about the first two inequalities that are listed out in the course plan. That is the AMGM inequality for two variables and the general AMGM for n variables. So this is something that most of you might be familiar with. So I'll just get started. The first inequality that we are looking at is AMGM, which is the arithmetic mean geometric mean inequality. And it says that if there are positive real numbers, if there are positive real numbers a and b, then we have a plus b by 2 is greater than equal to root of ab. Now, this is called the am of these two numbers, and this is called the gm. Now, this is obviously true because you have a minus b whole square is greater than equal to 0, and therefore a square plus b square is greater than equal to 2ab. Correct? And that just actually we should write it in terms of a plus b whole square. So we can write it like this: a plus b whole square minus 4ab is greater than equal to 0, and therefore that gives us a plus b whole square is greater than equal to 4ab, and that implies a plus b is greater than equal to 2 root ab. So this is only defined for positive real numbers. And if you have a situation where a is equal to b, if a is equal to b, then this becomes equal. So the inequality becomes an equality. So you have a plus b by 2 is equal to root ab in that case. So I'm sure everyone is familiar with this one. So a typical example of this could be prove that a square plus b square plus c square is greater than equal to ab plus bc plus ca. So what you can do is just prove that a square plus b square is greater than equal to 2ab, which is directly from AMGM. And similarly, how does it come from AMGM? Everyone should be aware of that. So it is basically a square plus b square by 2 is greater than equal to root over a square b square. So then it follows. Similarly, b square plus c square is greater than equal to 2bc, and c square plus a square is greater than equal to 2ca. And now adding all the left hand sides of this, you will get 2 times a square plus b square plus c square is greater than equal to 2 times ab plus bc plus ca, which follows from where this inequality comes, right? So that is the basic AMGM inequality. What about the general AMGM? The general AMGM inequality comes like this: a1 plus a2 plus, it is for n variables, a2 by n is greater than equal to nth root of product of all of these till n. Now, what we will do is look at a proof for this, proof of this inequality. And the proof that we are going to follow is Cauchy's proof by induction. So this is not a typical induction that we will do. Cauchy's proof by induction proceeds a little differently. And there are 3 steps to this, right? The first is the base case, which is fairly common. The second is if P of n is true, prove that implies P of 2n is true. So prove that if you can prove P of n, which is the statement that the inequality is true for n variables, then you prove that from n variables you can go to 2n variables also is true. And the last step is prove that Pn implies P of n minus 1. So basically what are we doing? We are saying that base case is proved. Then we are saying assume Pn, you can go to P2n, right? Okay, so that is good. That helps us climb up the staircase. We can go and prove for any higher powers of higher numbers of variables. Also, there is a third step which says that assume Pn, you can go to Pn minus 1. So then if this third step is true, then from here you can prove it for all the way down to base case P2, right? So that will cover everything, because after this you can go till here, and from here you can come down again using the third one, right? So this is the way the Cauchy's induction works. Let's now prove this. So the base case we have already proved. P2 is already proved. That is the basic AMGM. which is basically a plus b by 2 is greater than equal to root ab. We can even prove p3 also. P3 can be proved. If you have to prove this, you have to prove this thing is greater than equal to cube root of abc. Now, a very easy proof of this, if you take a is equal to x cube, b is equal to y cube, c is equal to z cube. This implies you have to prove x cube plus y cube plus z cube is greater than equal to 3xyz. Now that is easy because you have the factorization of x cube plus y cube plus z cube minus 3xyz as x plus y plus z, x square plus y square plus z square minus zx minus xy minus yz. Now this part can be shown to be half of x minus y whole square plus y minus z whole square plus z minus x whole square. And this is x plus y plus z. Now this is always positive. It could be 0 if x is equal to y is equal to z, right? In that case, the inequality becomes an equality. But otherwise it is positive. And this part is also positive because by definition, we have said that a, b, c were positive. A, B, C, which is x cube, y cube, z cube, we had said was positive. So the whole thing is positive. The RHS is positive. Therefore, you have proved that x cube plus y cube plus z cube is greater than equal to 3xyz. Equality happens when all three numbers are equal. And that is the same thing as saying that a plus b plus c is greater than equal to 3 cube root of abc, which is the P3 case, right? So now what we'll do is prove the step 2 and the step 3. Step 2 was saying that Pn implies P of 2n, right? So what does Pn mean? Pn means a1 plus a2 plus an by n is greater than equal to nth root of a1, a2 till an, right? Now, how can we prove that this means P2n? So let's write what P2n means. I mean, we will not write the whole statement. We'll just write a1 plus a2 till an plus an plus 1 plus 2 till a2n, right? Now, clearly, you can group it into two parts. This has n terms and this has n terms. Now we know that Pn is true. Pn is true. So this is true. So we can say that this is greater than equal to nth root of a1, a2 till an plus. Basically, I'm saying this inequality is true. This part is greater than nth root of n times actually nth root of this plus this inequality is also true n times nth root of an plus 1, an plus 2 till a2n, right? Are you understanding what I'm saying? I'm saying group these into two n terms and do AMGM for n variables here and do AMGM for n variables here. So that implies that the whole thing, which is the left-hand side of P2n, is greater than these two things, right? Now, on the next screen, what I will do is apply AMGM on these two. AMGM on these two, right? And that will give me something. So I'll just write everything here. A1 plus A2 plus A2n is greater than equal to, so far we have this, plus n times nth root of an plus 1, an plus 2 till A2n. Okay. Now applying AMGM on these two, we know that it is greater than equal to 2 times. You can do the calculation, it will come out like this, 2n, a1, a2 till a2n. How are you doing it? We are saying this is x, this is y, so must be greater than equal to 2 root xy. The 2 root xy is what I have written here. It is 2n times 2nth root of a1 to 2n product, right? Okay. Now this thing, correct? This thing immediately implies P2n because now we can say that a1 plus a2 plus a2n by 2n is greater than equal to 2nth root of a1, a2 till a2n. So this is our proof of the statement P2n is true now. So we started with Pn and we have proved that P2n is true. So step 2 for us is over. And now we move on to step 3 of the induction, where we have to go down. We have to assume Pn and prove that this implies Pn minus 1, right? So what have we assumed? We have assumed A1 plus A2 plus An by n is greater than equal to nth root of A1, A2 till An, right? Now this relation is true for all values of A1, A2, An, no matter what values of A1, A2, An we have. So we can pick any value for any of these terms as long as they are positive real numbers, right? So what we do is we let An be equal to n minus 1 root of A1, A2 till An minus 1. So basically, now we have a particular value of this An, which is n minus 1 root of A1, A2 till An minus 1, right? So now we can say that A1 plus A2 plus An by n is greater than equal to nth root of, I'm just writing this expression, but I will replace An with this thing, right? So I'll say A1, A2, An minus 1, and then n minus 1 root of A1, A2 till An minus 1, right? Now this part, notice the powers here, 1, 1, and there is power 1 by n minus 1. So the entire power for every term inside becomes 1 plus 1 by n minus 1, which is n by n minus 1. So I'll just write it like this, n A1, A2 till An minus 1 to the power n by n minus 1, which becomes equal to A1, A2 till An minus 1 power 1 by n minus 1, right? And now we are very close to the proof. We say that this is A1 plus A2, An minus 1 by n plus An by n is greater than equal to this thing, right? Now, this thing is actually An, right? This is actually An. We have defined An to be this. So it's greater than equal to An. So now this becomes greater than equal to An 1 minus 1 by n, which is equal to An into n minus 1 by n. So this side I have A1 plus A2 till An minus 1 by n. N cancels, and we have, when you bring this side, it becomes by n minus 1 is greater than equal to An. So this statement implies, okay, I'll just write it on the next screen. I have proved so far A1 plus A2 plus An minus 1 by n minus 1 is greater than equal to An, but An was equal to root of n minus 1 for A1, A2 till An minus 1. So this is my statement for Pn minus 1 actually. If you think about it, this is n minus 1 variables AMGM, right? So what I have done is I have proved P2, P3. I have proved from Pn you can imply P2n, and I have also proved that Pn implies Pn minus 1. And that completes our induction process. And now we have the generalized AMGM inequality with proof. We say that this is always greater than nth root of A1, A2 till An, right? Now, this inequality is super useful. We will find applications for this in many cases. I will just do a few problems to reiterate the concepts. So, for example, very easy examples these are. Suppose A1, A2, An are positive. You can prove, and A1, A2 till An product is equal to 1. We can prove that 1 plus A1, 1 plus A2, and so on, 1 plus An is going to be greater than equal to 2 power n. Now, this is very obvious because you can do AMGM for each of these brackets, and it's greater than equal to 2 root A1, 2 root A2, and so on, 2 root An, right? There are n brackets, so 2 power n comes, and product of these numbers is 1 given in the question, right? So we can prove this immediately. So let's look at another one. Another example for this could be prove that A plus B, B plus C, C plus A is greater than equal to 8ABC. Again, very straightforward. Just say it is greater than 2 root AB, 2 root BC, and 2 root AC, and multiply them. We are doing AMGM on each of these, right? And that proves the whole inequality. What about this one? Let's see. prove that a cube by b plus c plus b cube by c plus a plus c cube by a plus b. Okay, I've made a mistake here. This is not like this. This is a cube by bc plus b cube by ca plus c cube by ab is greater than equal to a plus b plus c. Let's say we want to prove this. So I want to use AMGM, but directly, if you try to use AMGM on these three terms, it will come out with 2 by 3 powers and all. The powers will not resolve themselves nicely. So what I want to do is apply AMGM in a clever way so that I don't get any roots, right? So on what term can I apply a cube by bc? A cube by bc I have to use in an AMGM inequality. What should be my other terms with which I can combine it, right? So imagine a cube by bc and b and c if you do AMGM, right? So this plus this by 3 should be greater than equal to cube root of a cube by bc into b into c, which cancels and it becomes a, right? So what you can immediately prove is that a cube by bc is greater than equal to b 3a greater than equal to 3 times a minus b minus c. And similarly, this is greater than equal to 3 times b minus a minus c. And this is greater than equal to 3 times c minus a minus b. If you add all of it, this will come greater than equal to 3 times a plus b plus c minus 2 times a plus b plus c, which will be equal to your a plus b plus c. So you understand that sometimes you have to be a little clever about the choice of the terms on which you will apply AMGM. We'll see more applications of this type as we go ahead. Right now, I just wanted to show you some easy examples by which we can focus on the concepts and make sure that we understood them. So we have covered 2 inequalities. There are in total 14 inequalities that we want to cover. The next inequality that we will look at in the next video will be weighted AMGM inequality and also Cauchy sorts. So we will go ahead with that in the future videos. Stay tuned. I hope you learn something from this course. See you next time.